Lesson 6.4 is about solving trigonometric equations using identities. So let's prove that algebraically that the left side equals the right side. So I'm going to start with the left side and see if I can get it to look somewhat like the right side. And if I get to a certain point and it's as simple as I can go, then I'll start with the right side. So I always start with one side, and then once I've done as much as I can, then I switch sides if I have to. So 2 tan x, we don't, all we're going to do is replace tan of x with sine x over cos x. Divided by, again, we can write 1 minus tan of x, tan squared x, we can write it as 1 minus sine squared x over cos squared x. So that's going to be the left side so far. So the top I can't really do anything with, but I am going to get common denominators with the bottom, so I'm going to divide by in brackets. It'll be 1 can be multiplied by cos squared x, top and bottom. So that's the same thing as saying 1, and then you're subtracting sine squared x over cos squared x. So now we're going to write it as one common denominator. Over cos squared x. Our next step will be to flip that second fraction. So I'm going to multiply it by cos squared x at the top over cos squared x minus sine squared x. So I can cross off a cos and a cos from the top. So cos from the bottom, cos at the top. So I'll use red for that. So that can cross each other off as factors, leaving me with 2 sine x cos x at the top over cos squared x minus sine squared x. If you guys go to your formula sheet, that's where you can replace the double angle. You can actually go and write 2 sine theta cos theta with 2 sine 2 theta. So this is the identity that I'm looking at. So I'm just going to write it to the side. So sine 2 theta is equal to 2 sine theta multiplied by cos theta. So as you can see at the top, I have the right side. I'm going to rewrite it as sine 2x. And as you can see, now it equals the same as the right side, so therefore left side equals right side, and I've just proved that that is true. So the identity is true. Now going on to our new lesson 6.4, where it says we want to solve trigonometric functions. We need to make substitutions using trig identities. Then once we have done the substitutions, then we can actually replace and solve for the solution. Okay, so you want us to make it as simple as possible first. Once it's simplified, that's when we'll solve for the value that the left side or right side is equal to over the domain given. So in the question in step A, or in example 1A, they're giving us a double angle, which we don't like to work with. So we're going to replace sine 2x with 2 sine x cos x. And then we still have this minus cos x equaling 0 that we have to write. Next step, I'm going to factor out the cos x that's common for both of those terms. So this makes it way easier to solve for where cos x equals 0 and where 2 sine x minus 1 equals 0. Well, cos x we know is 0 always at 90 degrees and 270. So where x is equal to pi over 2 within the domain of 0 to 2 pi, so we're in radian mode. And 270, which is 3 pi over 2. So this is on the quadrants. We're talking about this answer and this answer. So that's pi over 2 and 3 pi over 2 if we're looking at the coordinates of it. And here we're looking at where sine of x is equal to 1 over 2 when you solve for sine of x. So step 1 is we can go in radians, or sorry, in degree mode. In degree mode, you can find that the reference angle is 30 degrees. Now that means that x could equal pi over 6. So we want to know where sine is positive. Well, sine is positive in quadrant number 1 and in quadrant number 2. So in quadrant number 1, the answer will be then pi over 6. And in quadrant number 2, we would have to go pi, which is 180, minus the reference angle, pi over 6. So that's going to be 6 over 6 pi minus pi over 6, which is 5 pi over 6 as our solution. So these are our two answers for where sine is equal to 1/2. Okay, so those are all the solutions. We had 4 solutions for example A. Example B, so far we have 2 cos x plus 1 minus sine squared x, and then we'll bring that 3 over to become minus 3. If you look, this right here can be replaced with cos squared x. So we're going to rewrite it as, in standard form, when we're talking about a quadratic function, we're going to put the squared value first, then the 2 cos x next. And then we have minus 3 equaling 0. If you look at it, this is the same as saying x squared plus 2x minus 3 equals 0. So that's how you could replace it to make it easier for you to look at. Well, if you were to factor this, this would be where x plus 3 and x minus 1 equals 0. So if you were to factor x squared plus 2x minus 3, you get x plus 3, x minus 1. So that is where cos, you're going to replace x with cos x now. Those are the factors now that you have. And then cos x minus 1 equals 0. So since we made it easier to look at by replacing x or cos x with x, you have to replace that back in. So now we know that cos x equals -3, which is actually not possible. You can't have a value of cos being greater than -1, or greater than 1 and less than -1. So that doesn't exist. But where cos x equals +1 does exist. If you look at your quadrantal angles where you have 1, 0, this is where the x coordinate is 0, and that's going to occur at 0 degrees. So when x equals 0, that is a possibility. So that's our only solution for example B. Example number 2, we're going to solve for the equation. As you can see, I'm going to start with the right side first in order to simplify this and then algebraically solve over the domain. So I'm going to replace tan with sine x over cos x. The reason being is that the cos x's will cross each other off, leaving us with sine squared x equaling 1/2 sine x. You can bring it all to one side, but in order to make it easier, I'm going to get rid of the fractions by multiplying everything by 2. So now you're going to have 2 sine squared x equaling, these 2's will cross each other off, leaving us with just sine x on the right side. Now we're going to bring everything to one side because we have something squared. And I'm going to factor out the sign that's common for both. So as you can see, sine x could equal 0, or sine x could equal 1 over 2. So those are the two values that I have to solve. And then this one I want to solve in degree mode. Okay, so they're asking us, when is sine x equal to 0? So when we're looking at our angles, that's where the y-coordinate is 0. So we know that the y-coordinate is going to be 0 at 0 degrees, 360 degrees, and then over here, the y-coordinate is 0, and that's going to be at 180 degrees. So using the domain that they've given us, we know that x could equal 0, 180 degrees, or 360 degrees. And for x, for the second part, where sine of x equals 1/2, I always like to find it by doing the inverse of 1/2, and that's going to give me the reference angle. So the reference angle is 30 degrees. So we know that we're trying to find where sine is equal to a positive value, and so that's going to occur in quadrant 1 and quadrant 2. So in quadrant number 1, we know it's equal to the reference angle, so we know that one answer is 30 degrees. And then in quadrant number 2, we're always going to go 180 minus the reference angle, so that's going to give us 150 degrees as our second answer. Okay, so we have 0, 180, 360, 30 degrees, and 150, and all of these will work to make left side equal to right side. Example number 3, we're going to rewrite that double angle. So instead of cos 2x, we're going to write it as 2 cos squared x minus 1. So as you can see, I can bring everything to one side and make it a quadratic equation. So once it's equal to 0, now you can factor it as if it was 2x squared minus x minus 1 equaling 0. So the factors that make this up would be 2x plus 1 and x minus 1 equaling 0. So once you put cos back in, it'll look like this. So that's one factor, and the other factor is cos of x minus 1 equals 0. So that means that cos x could equal negative 1/2, or cos of x could equal positive 1. So in this case, when you're looking at the reference angles, I'm going to go into degree mode just to make it easier to solve for it, and then I'll convert it to radians. So I'm going to go cos inverse of 1 divided by 2, and I get that that is in radian mode, or sorry, in degree mode. Cos inverse of 1 divided by 2 is 60 degrees. And that's equal to pi over 3. So now that you know that that occurs at pi over 3, we're looking at where cos is negative. C-A-S-T, that's going to occur in quadrant 2 and 3. So in quadrant number 2, we're going to have to go pi, subtract pi over 3. So that just means that it's going to be 2 pi over 3. And then in quadrant number 3, we're going to have to take pi and add pi over 3. So that's going to equal 4 pi over 3. And then our next answer is where cos of x equals 1. So again, we're looking at those quadrantal angles. I always like to label them to start off. So we're looking at where the x coordinate is 1, and that's only going to occur at 0 degrees and then 0 radians. Now, what we need to also do is the general solution. So this is asking for the general solution for all of this. So for the first one, we would just say, well, every 2 pi, we're going to have an answer. So we would say 2n pi, where cos x equals 1. Okay, so and n can be every integer. So that's one way of saying that it's going to occur at 0, then at 2 pi, then continuing on until we go around the circle, either going clockwise or counterclockwise. Then we're going to have the smallest x value that we have also is then 2 pi over 3 plus, to go around the circle, 2n pi. N is an element of the integers again. And then finally our last one, we're taking 4 pi over 3 and adding a full rotation around to get again to that coterminal angles. So all the coterminal angles, if you add 2 pi to them, that'll take you back to that same position, and this will go around where it shows you the general solution. Okay, so this is our final answer for the general solution for this question, where we use every answer and we just add 2n pi. So the first one was 0 radians, so that's why we added 2n pi, and we got that value. Same thing for the next ones. We just took 2 pi over 3 and 4 pi over 3 and added the 2 pi times n, because n can be any integer, either going +1 or -1 and so on. Example number 4, we're going to replace secant with 1 over cos of x. So what I'll do in this case is, because I have it in the denominator, I'm going to multiply everything by cos of x to get it in the numerator. So it'll be 3 cos squared x, so everything is multiplying by cos of x. Then 2 cos of x equaling 5 over cos of x times cos of x. So these guys will cross each other off. So that was the situation where I wanted to get rid of the fraction. And that leaves you with bringing 5 over a quadratic equation. So we want to factor this and see where this is possible. So this would be like saying 3x squared plus 2x minus 5 equals 0. So we want to look for two numbers that multiply to -15 and add up to 2x. So in this case, two numbers that multiply to -15 and add up would be 5 and -3. So then using my the way I like to factor is I like to always take the leading coefficient, write it out twice with the variable. So in this case, my variable is x squared over the numbers you just found, which were 5 and -3. So with these values, I know that one factor is going to be 3x plus 5, and the other one is going to be just x minus 1. So those will multiply to give you that, and then you'll replace the x with cos of x. So that gives us cos of x equals -5 over 3, and cos of x equals +1. So in this one, I'm going to make sure that I'm in radians mode when I do this question. So I'm going to do cos inverse of right away I know that if the numerator is higher than the denominator, this is not going to exist. So this answer right here doesn't exist. Negative 5 over 3, if you try to do the inverse of that, it doesn't work within the domain. So the only one I'm looking for is where cos of x equals 1. And I know that's going to occur at 0 degrees, then at 2 pi, and then so on. So I know that the solution, the general solution, is going to be 2 pi n or 2n pi, however you want to write it. I'm going to write it with the pi going in front of the variable. So 2 pi n, and then n is an element of integers. So that would be my answer for example number 4. And our last one, example number 5. We'll replace those double angles with, for example, cos 2x. We can replace it with cos squared x minus sine squared x. And then we're multiplying it by cos of x. And then instead of sine 2x, we're going to replace it with 2 sine x cos x. So what I've replaced has gone in the brackets. Everything else stays the same. Next, I'm going to distribute this cos into the brackets and then the sine into the brackets. And then the negative will also go into the brackets so that I get rid of the brackets. So it'll be negative 2 sine squared x and then cos of x equals 0. Now this can be replaced with 1 minus cos squared x. So I'm going to replace that. And then if you'll notice, before I do that, these two are the same. So these are like terms. So I'm going to put them together by adding them together. So I have a minus 1 even if I don't see it. So it's going to be cos 3x or cos x to the power of 3 minus 3 sine squared x cos x equals 0. And then this is where I'll replace sine squared x with 1 minus cos squared x. So it'll be cos cubed x minus 3, 1 minus cos squared x, and then cos x equaling 0. Now I'm going to multiply the negative 3 into the brackets and the cos into the brackets as well. So it's going to be minus 3 cos x for the first term because it's multiplying by 1. And then it'll be positive 3 cos cubed x equaling 0. So I did that because now I can actually join together these like terms here. The 3 and the 1 in front of it can become 4 cos cubed x minus 3 cos x equaling 0. Now I'm going to factor out the cos, so that's going to give me cos x in front of the brackets, leaving me with 4 cos squared x minus 3. This is the point where I can split it up and say, well, cos of x, when it's equal to 0, that will give me solutions. And if you solve for the second part, cos x could equal 3 over 4. So we're dividing, or we're adding 3 to both sides and then dividing by 4 squared. We're going to have to square root both sides, and that gives me where cos of x equals positive negative root 3 over 2. So when you square root that, you get square root of 3 over 2. So this one algebraically wants you to determine the number of solutions for the equation over the domain of negative 360 to positive 360. So they want to figure out every time that this can occur. So let's look at the first one. So they're not asking what the solutions are, they're asking just how many solutions there are. So where cos is equal to 0, when we have our angles, that's where the x-coordinate is 0. So that's not going to be here. So we're going to have 0 when x is equal to 90 degrees and 270 degrees. Now that's going to be from 0 to 360. So from 0 to 360, we have 2 solutions. And that means from negative 360 to 0, we have also 2 solutions. So from the first set, we have 4 solutions. Okay, so we have 4 solutions from cos x equaling 0. Now we have to look at the next one where whenever you have a positive negative answer, that means it can occur in every quadrant. You're going to have a solution in every single quadrant. So from 0 to 360, you're going to have 4 solutions. And then from negative 360 to 0, you're going to have another 4 solutions because it always repeats itself. And so all you have to do is count. There's 4 solutions from the other one, 8 solutions from the cos x equaling positive negative root 3 over 2. So together, therefore, total of 12 solutions. Okay, so that is it for lesson 6.4. So if you would like some additional practice, there are practice questions below that summarize 6.3 and 6.4 in the notes, but try some homework questions.